Hello students, welcome back. Let's go back to section 3 and complete it. Here's a brief recap. First, we started with a solution of a homogeneous linear ODE with constant coefficient, y of t, and then from this equation, we take the Laplace transform and do some algebra. That way we can prove capital Y of s, the Laplace transform, is equal to a proper rational function r of s over q of s, where q is the characteristic polynomial given by these coefficients, and of course it has degree n, and r of s is a polynomial of degree at most n minus 1, so that this whole thing is proper. And then, upon taking the Laplace inversion, that we come back to the original. So we begin with y, presumably, and then we go to capital Y equals to that, and then we come back to y. Along the way, capital Y can be written like this so that this Laplace inversion is meaningful, and that proves y of t exists and unique with respect to the initial conditions and so on. It's a huge accomplishment, but there's more. How do we calculate this Laplace inversion? Well, if we have specific rational function, we can do it. In general, how do we do that? And that's where all these were necessary. Complex number system, especially the fundamental theorem of algebra, which says any complex polynomial can be factored completely down to linear factors, either this form or that form with identical factors repeated. As for real polynomials, we need a couple more steps. If we have a complex zero, then its conjugate is also 0. We did that. And then, using all those, including the fundamental theorem, we can prove that any real polynomial can be factored completely down to either linear factor or quadratic irreducible factor. And more, the quadratic irreducible factor can be rewritten as complete square plus square form. The idea was like this: completely factor using the fundamental theorem of algebra, and then we begin from the left. If they are already real, move on until you reach a first complex root, which can be the very first if you're unlucky. And then it must have the conjugate somewhere, so bring those up, put those together, and then do some computation. Then you can prove that this part can be rewritten as complete square plus square form. So that was the idea. So for complex case, the fundamental theorem of algebra was sufficient. For real case, we need to go a little bit further, but still, we don't have any worse than quadratic irreducible. Now, we use those to establish the general solutions of the homogeneous equations. The complex case, everything can be factored complete to the linear factor. So look at this in the denominator, and then consequently, we'll have the partial fractions like these. And consequently, we have this kind of linear combination. Any solution can be written as linear combinations of these, and these are so-called the basis function. So start from some blues and then some other colors, in the end some greens. And total, there are precisely n of them because, these powers add up to n. For reals, it's a little bit trickier because we have to consider quadratic irreducibles as well. But if you take these red parts and look carefully and work out, then you get exponential sine cosine times t to whatever power. And those form the basis functions. And every solution can be written as a linear combination of those. And that's what we just established. Now, here's some other questions. Are there any other ways to get the general forms? Any other base? How do you know we have those bases? If we have n unknowns and then n undetermined coefficients, and n linearly independent solutions, then will that be enough? Where there are many other questions. And in order to answer those questions, we'll have to do these. Well, I take it back. We don't really have to do this. This is a effective way to do it, as a matter of fact. Back in way later in chapter 4, I do something similar, but not exactly the same, and still I managed to get through it and then establish what we want to do without going through all those rigorous details of linear algebra as we have here. So I don't say this is necessary, but it's a good way anyway. In any case, this is the path our textbook author took, so let's talk about it. Okay, ready? Okay, recap is done, and this is a real topic. Okay, ready? All right. Let's begin with a set called RQ. An RQ is a set of all proper rational functions with denominator Q of S. That is R of S over Q of S, where degree of R of S is strictly less than Q of S. Now, it is possible to prove that RQ is a linear space or vector space. And you don't have to go through its all 9 properties of vector space, actually, because we already know the function space is a vector space. So all we have to prove is that this is a subspace. Is it closed under linear combination? Well, A1 and then rational plus A2 times another rational, and denominator is the same, so we just have A1R plus A2R2 form in the numerator. And if you look at the numerator and get the degree, it has to be less than the degree of denominator, because all we have is just multiplying by constant and taking like terms together. We're not increasing the degree. We're not multiplying by S or something like that. So yes, it is closed under linear combination, and this is a linear space. So we can consider its generators and linear independence and so on. And to make the long story short, we can conclude like this. One over Q of S, S over Q of S, S squared over Q of S, and so on. S to the nth minus 1 power Q of S. It turns out this is a basis of that. It is easy to prove that this generates that, because this is a polynomial here, and polynomials are generated by linear combination of 1 as s squared over Sn minus first power. That's the way polynomials are. No problem there. As for the linear independence, that's a little bit tricky, and that it may need a bit of computation, but it's not too bad. After all, the denominator is all the same, so this isn't too bad. Let's see, let's replace this by plus, replace by plus, replace by plus, and then let's put some coefficients here. C is 0 times that, 0 times that, and then let's write it s to the 0 power, and then C 1 times that, and then this is s to the first power, and so on. C 2 times that plus C n minus 1 times that, and that is equal to 0. But then again, equal to 0 functions, so we have to write, as a matter of fact, identically, constantly 0. Set up like this. Shall I expand the font a little bit? Okay, set up like this. But then again, denominators are all the same, so we can cancel these out, as a matter of fact. And then what do? We can plug in some s values in there. S is equal to 0, 1, and so on and so forth. Any numbers will do actually. That's as good as any. And then plug those in, and then you're gonna get a system of n linear equations with n unknowns, C0, C1, C2, all the way up to Cn minus 1. It's not difficult to prove they all must be 0. I'll leave the details to the student. And if you want a little bit more elegant proof, you can do mathematical induction too. In any case, this is a basis, and thus the dimension of RQ is n. This is a conclusion I can draw. Okay, all right. We got that. The details are left to the students. Okay, next, let's introduce another set, EQ, and it's an image under the Laplace inversion of RQ. In other words, Laplace inversion belongs to RQ. So if I take forward Laplace transform, and that belongs to RQ, that's equivalent expression. But even more importantly, it is equivalent to the set of all solutions of the original ODE. As a matter of fact, let's go back to this. You see, we started from the original solution of the original ODE, went back to Laplace transform, and then we got back to Laplace inversion. And turns out R over Q along the way corresponds to the solution. So EQ came from RQ, which is R over Q. Therefore, we actually came back to the set of solutions of the homogeneous equations. Now, if you just describe EQ only with these, and can we consider the dimension and so on? It is possible actually, and I do that in week 9, I think, in chapter 4. But the path our textbook author took is kind of a little bit winding fashion, starting from RQ, and then got to this EQ like this, and then note these two are the same. And then we can establish the dimension of EQ is n like this. Oh, by the way, EQ is a vector space as well because it's an image of a linear map, so it's a vector space, or you can prove it directly as I have in this sketch. So this EQ is image of this Laplace inversion. Okay. And then also, look at this, dimension of the image, kernel first, kernel of the Laplace transform plus dimension of image of the Laplace transform has to be equal to dimension of the original space, RQ. This comes from the rank theorem. And then, what is the dimension of the kernel here? The Laplace transform and the Laplace inversion, they're both one-to-one, so kernel should be just trivial. So dimension of kernel is actually 0. And then the dimension of image, what is this? This is EQ. So this is dimension of EQ. And that's equal to dimension of RQ, and that's n, as we saw before. That's the basis. So dimension is n. And by the rank theorem, dimension of EQ is also n. Let's see, does it help? Let's go to BQ, which are the standard basis, and then those are these functions we discussed over here. These, or functions of these form. And in real number system, these functions. Exactly the same function that appear here, or in this form. Now, how many are there? This one is easier to count because of the fundamental theorem. This has to be precisely n factors, counting all the multiplicities. So if I add up all those m's, I should get precisely n, so there are precisely n such numbers, such functions here. So dimension is n, and then we have BQ that belongs to EQ that generates all this. You see, we proved every solution can be generated by these, by linear combinations. So yeah, EQ is this. And then what do we have here? Dimension of EQ is n, and that's precisely the number of these, number of elements of these. So these generate EQ, yeah. And then the number of generators equal to the dimension, they have to be linearly independent as well. They are the basis. Remember, the dimension is minimum number of generators and also maximum number of linearly independent elements. So dimension, so these are linearly independent too. And this is actually basis. BQ is actually basis. We can do something similar with R as well. A little bit trickier to count because this quadratic irreducible split into two, but it's not difficult to see. The total number is n, so yeah, same thing applies there. So, whenever we have n generators, then that's a basis. Here are n generators. Here are n generators, that's basis. And here's another n generators, that's basis. So in C and in R, they look completely different. But in terms of EQ, then perfectly fine. Because of those dimension analysis. Also, if you happen to find another set of solutions that are linearly independent, and the number happens to be exactly the same n, the dimension, then they're going to generate as well. So those kind of conclusions come from this dimension analysis. One more thing, because of that, we don't really have to prove that the set is linearly independent. To prove that, that's enormous work as a matter of fact. This one, even worse work. We don't have to do any of those because of those dimension analysis. In any case, this is a path our textbook author chose and got pretty close completing. And I think I didn't really complete it, but I got down close completing it, I guess. But then again, as a matter of fact, what I just did is going over about 2/3 of linear algebra, 2/3 of entire course in just under 20 minutes. It's enormous. I guess I'll have to stop here. Cannot add any more.